Now, so we'll start off then with, we want the active power transmitted to the rotor. Uh, and so that is PR. And so if you remember from our power flow, PR is equal to P in, which is electrical, and so that value has been specified. Subtract the stator losses. And very often the stator losses will be supplied to you as two different values because there's a copper loss in the stator and an iron loss. And here, you've just been given that the copper and iron loss in the stator total 5 kilowatts. So you just got the total for that. So PR then is equal to our electrical power drawn from the feeder, or P in, at 80 kilowatts. Subtract the stator loss of 5 kilowatts. And so PR then is equal to 75 kilowatts. Part B, we are asked to find the rotor I-squared air losses. So remember, the rotor I-squared air loss is what we've been calling PJR. And PJR is equal to the slip multiplied by PR. Okay, which means we got to know the slip. Well, we can find the slip, right? Because we've been given the information to find that. And so remember, slip is equal to NS minus N divided by NS times 100%. And because we need the slip as a decimal, for this particular part, we can ignore it 100% if we wish, and calculate the slip as NS. Right, we're told the sink speed is 1200 RPMs. Subtract the running speed, which is 1152 RPMs, and divide it by 1200. So the slip speed here is 48 RPMs, and that's the numerator. And that's divided by 1200. So the slip as a decimal is equal to 0.04, which of course is 4%. Okay, so based on that then, we can find PJR, right? Because it is 0.04 multiplied by the power delivered to the rotor, which was 75 kilowatts. And so the rotor I-squared air loss, PJR, is equal to 3 kilowatts. Now, so, remembering that this is PJR, it just makes it a little bit easier writing that equation, so you don't have to keep writing out the rotor loss. Or remember, that is the rotor copper loss, or rotor I-squared air loss. Okay, now part C asks us to find the mechanical power developed. And so remember, when we use the word developed, that is PMI. And we have, some equations with torque and PMI in it. But here, remember, this is power flow, right? And so now that we have the copper loss in the rotor, PMI just comes from our power flow. And so what I'm trying to say is that if you follow the power flow diagram, PMI is equal to PR subtract the rotor loss. And remember that we only accounts for copper losses in the rotor, and so that value is 3 kilowatts, right? And so 75 kilowatts then minus 3 kilowatts. And so the mechanical power developed 72 kilowatts. Okay, part D then asks us for the mechanical power delivered to the load, and it gives us the shaft loss. So the power delivered to the load, member, is PM, which we normally call P out. And again, you know, that should be really close to the rating of the motor, which we weren't given here. But P out is equal to PMI, subtract that shaft loss, which we normally, I'll just write as windage and friction. And so we have 72 kilowatts minus the 2 kilowatts that we're given, and P out then is equal to 70 kilowatts. So now that motor, you know, that's a large motor. It's got a 70 kilowatt output there and 80 kilowatt input. And so there's 10 kilowatts of losses, and the rest of that we're led to believe is delivered to the load. Okay, so motor efficiency is easy now because we have both P in and P out. And so I'm going to put the efficiency calculation over here now. Efficiency is equal to P out over P in. And so again, you know, we want to multiply that by 100% because efficiency is normally expressed in percent. And so efficiency then is equal to 70 kilowatts divided by 80 kilowatts of electrical power times 100%. And if you do that, you'll find out that that's really high with respect to most of the DC motors that we looked at. But this is a large motor, right? 70 kilowatts. And so that calculation suggests 87.5% for efficiency. And part F now, torque developed. We got two equations we can take that from now, right? And so the standard one is the one with PMI in it. But again, both of them got to give us the same answer, and so you can check that if you wish. But 9.55 multiplied PMI was 72 kilowatts, and running speed 1152 RPMs. And so remember now that when we go to our other torque equation, which is 9.55 times PR divided by NS, that got to yield the exact same value for torque developed, right? And so again, you know, you can check that it does, because if it don't, well, you know, there's an error somewhere. Okay, so that works out to, if we round to three significant digits, 597, and remember that the unit for torque is Newton meters. Okay, so now let's think about our power flow diagram. And like I said, if you follow along there in the notes on page 74, I basically said this, right? And so I'm just going to move that over now to that first page. And so right here, I should be able to paste that in there. And so we said that we wanted to sketch a power flow block diagram to represent the motor. Include the value of power and watts transferred at each stage and auto losses, each with a label. And so now instead of me trying to sketch that here, I went and plucked this out of my notes. And so let's bring that over to the main page here and stick that in. And I'll bring it down here. And now I want to blow that up a little bit. And so basically, this is the result of what we talked about, power flow in the notes, and trying to simplify the sketching of it. And so there's three main pieces that you should be including in this, right? The stator, the rotor, the shaft, the power in and out of each one, and auto losses. And normally the stator loss here will be given as two individual values. But for this example, they gave us one single value for the total. So then that's what we got, that's what we put on here. So the input power is electrical, and remember the arrow is important because it shows us the direction of power. 80 kilowatts into the stator. The stator losses then are, I'd call this the stator copper losses and the iron loss, and that totals 5 kilowatts. So then PR 75 kilowatts, and of course those numbers match our calculations up there. 75 kilowatts delivered to the rotor across the air gap. PJR is our rotor copper loss, and it's 3 kilowatts as we calculated. The rest of the power then, 75 minus 3 is PMI. 72 kilowatts is delivered to the shaft. It is the mechanical power developed. The shaft loss is windage and friction, 2 kilowatts. So 70 kilowatts is delivered to the load, and that of course is P out. Now, again, our labels for this would be windage and friction. This one is fine at PJR, but it is the rotor I squared R loss, or the rotor copper loss. And this one here is iron. And of course the stator copper loss. And really, if you just put down I squared R there and you don't bother with the stator part, because we know that it's the stator I squared R loss, right? And so over here again, if you don't want to write that down, just write down I squared R next to that value or that arrow, right? And so a value for each power listed, and a label, and the arrows to show the direction of flow through the motor. And that's our power flow block diagram.